In the second part of section 10.4, we're going to look at how inscribed angles apply to polygons and inscribed polygons. So first of all, we have mentioned this before. An inscribed polygon is any polygon where the vertices are on a circle. And the circle would be called the circumscribed circle because it is outside of an inscribed polygon. So inscribed, think it's inside. Circumscribed is outside. So this would be an inscribed pentagon here. Every vertex is on that circle. Here's an inscribed triangle, an inscribed right triangle actually, in that circle. And a theorem right away, if a right triangle is inscribed in a circle, as we have in this picture here, a right triangle in a circle, the hypotenuse is a what? Well, think about what we know about inscribed angles, because every single angle in an inscribed polygon is an inscribed angle. That's why it's called an inscribed polygon. And if I know this inscribed angle is 90, and I look at the arc that it intercepts here, okay, this is a 90-degree inscribed angle, and you know that an intercepted arc is double the angle, so if that's 90, this arc is 180 degrees. Wait a second, 180 degrees, that's a semicircle. Therefore, what do I know that this segment actually is? Doesn't that make the hypotenuse, which is this length, a diameter of that circle? Because a diameter is what splits a circle into two semicircles, and because this is 180, that is a semicircle. So if a right triangle is inscribed in a circle, you automatically have a hypotenuse being, you have a diameter as a hypotenuse. And the converse is also true. If one side of an inscribed triangle, let's say I did not know this was a right angle, let's just say I saw a triangle, but I knew that this was a diameter because it went through the center, then you would know that angle opposite from this side would have to be 90, because you would have a semicircle if it was a diameter. Therefore, that inscribed angle is half of 180, or 90. So the angle opposite from it would be right, and it would be a right triangle. Let's use that in a real-life problem here. You're taking a picture of a statue. This is like a overhead view, so you're looking down on some sort of statue. This green thing must be standing up, and the whole statue is this base, which is orange. And you know your camera has a 90-degree field of vision, so if you're standing here taking the picture, this is how much your camera can see is at a 90-degree range between the two, I guess, rays if you look to the edge of where the camera can take the picture. Let's say you want to photograph this statue, and you want to know where can you stand so the statue is perfectly framed. Like, you want this entire statue to be exactly in the picture, nothing around it. So from endpoint to endpoint. Think about what we just talked about here. I have a right triangle, and I want to know, is this the only place that I can stand to get that entire picture framed in that, the entire statue framed in that picture? Well, that can't be the only place to stand, the only place where a 90-degree angle works. But I want a very definite idea for where I can stand. Think about this. This would be, if I picture that circle, remember we're talking about a right triangle inscribed in a circle. If I make this a diameter, and then if I could create a semicircle here, I know that every single point on there would be a right angle. So I'm going to actually grab my circle tool from here. I think that's pretty close to the center. And of course it had to move. Let's see, okay, I'll have to adjust that a little bit, and then go back to full screen. Basically, I'm trying to make this circle fit perfectly at the edges of this statue here. Now notice the key points here. I have the edges of the statue being the end of the diameter, and the camera is right on there too. Anywhere on this semicircle, I could stand with that camera and take that picture, and I'd have a perfect 90-degree range. So anywhere on this semicircle. Because you know that if you have a diameter of a circle and you put a right triangle there, actually if you have a diameter circle, anytime that you draw a triangle, it's going to be a right angle, no matter what. You have a diameter, this would have to be a right angle because this is a semicircle and that's inscribed, so half of it. If you stand right here with the camera and you make two chords going to the ends of the camera, this would also be 90 degrees. Because again, this diameter means this is a semicircle, or 180, that angle has to be half of it. So anywhere in that semicircle would work. And you'd have that perfect right angle to the endpoints of that statue. Alright, this is a really cool theorem here. A quadrilateral can be inscribed in a circle if and only if its opposite angles are blank. So I have a quadrilateral inscribed in the circle. And I'm talking about the opposite angles. So I'll mark these opposite angles in red, how about? There's got to be something special happening with these angles. First of all, what kind of angles are these? Are all the angles in this quadrilateral? These are all inscribed angles. Since it's an inscribed quadrilateral, they're inscribed angles, and you know an inscribed angle is half of its intercepted arc, right? So this inscribed angle, its intercepted arc would be everything here. Right? That would be the intercepted arc of this angle here. What's the intercepted arc of this angle, the opposite one from it? Well, this inscribed angle has endpoints here and here, and its intercepted arc would be here to here. Right back to the same endpoint. Wait a second, I just did the full circle. So wait, these are inscribed angles. And you know, inscribed angles are half the intercepted arcs. But the intercepted arcs in this case are the full circle. So these inscribed angles are half of their intercepted arcs, and together the intercepted arcs are the full circle. And what does a full circle measure? 360 degrees. So together these angles measure not 360, but remember, inscribed angles are half of those arcs. So half of 360 together, these angles add up to 180. What is that called when you have two angles that add up to 180? They are supplementary. Again, the reason why, because this inscribed angle had this intercepted arc, and its opposite inscribed angle in that quadrilateral had this intercepted arc. Together, their intercepted arcs were the whole circle, which is 360. But since they're inscribed angles, they're half of the 360, so together they must combine to 180. And we can see the same thing happen if we look at this pair of opposite angles in blue. If I look at this one, the inscribed angle makes this intercepted arc. So right here, this inscribed angle has this intercepted arc. And again, we've made the full circle, which is 360, but these are inscribed angles, and they're half of 360. So together, they would add to 180. So it's kind of neat. A quadrilateral is inscribed in a circle. You know the opposite angles have to be supplementary. And don't forget, these are still inscribed angles. They're still half of their intercepted arc, and that can help us find unknown arcs sometimes too. So let's find the value of each variable here. What do we know? Opposite angles should be supplementary. So 100 and x should add to 180. Therefore, I know that x has to be 80 degrees. 180 would be 180. I know that these opposite angles have to add to 180 because, again, their intercepted arcs would be the full circle, which is 360. They need to be half of that. So to find angle y, I'm doing 180 minus 160. Excuse me, 180 minus just 68. And I get 112 degrees for y. And that looks a little bit off because the picture must not be drawn to scale. This is not 100 degrees, and this is not 80, but we'd have to assume that we're right here. It's just not drawn to scale. Y looks like it could be 112, though, so that looks good. All right, what about here? We have an inscribed quadrilateral, which we know means the opposite angles have to be supplementary or add to 180. So a little bit trickier. I know this angle plus this angle would equal 180. Let's set up the algebra here. So 5x plus 3 plus 7x minus 5, together they add up to 180 degrees. Combine like terms. 5x and 7x is 12x. Positive 3, negative 5 would be minus 2 equals 180. Add 2 to both sides. 12x equals 182. And 182 divided by 12. X is 15.1 and the 6 repeats. Not a nice answer, but I guess that's what we're getting there. And what about for y? I know in a quadrilateral inscribed in a circle, the opposite angles have to be supplementary. So these two would have to add up to 180. Again, because they're inscribed, so they're half of their arcs, and the full arcs of both would be the whole circle, so half of 360. So 19y plus 17y would have to equal 180. I'm sorry. And 19y plus 17y combined like terms, that's 36y equals 180. And then do 180 divided by 36. And y equals 5. Nicer answer on that one. So in this section, we're looking at, first of all, if a right triangle is inscribed in a circle, you have the diameter being a hypotenuse. And if you have an inscribed quadrilateral, the opposite angles need to be supplementary.